When traffic surges in a high-volume digital environment, failure rarely starts with a catastrophic crash. It begins with friction. Nodes slow down, queues fill, and the infrastructure seizes under the weight of interconnected dependencies. At the origin of this infrastructure is a standard business action. A user clicks a button, expecting an instantaneous confirmation. This node link diagram illustrates that a single action fans out across dozens of discrete service boundaries. Every network hop introduces latency. Milliseconds stack sequentially. Relying on synchronous patterns ensures delays compound. Services waiting in line blow past acceptable limits, causing severe lag. Contrast this failing state with the engineering standard for high-performance RPC calls, a target of roughly 30 milliseconds at the P50 latency mark. Reaching that 30-millisecond threshold is mathematically impossible through code optimization alone if the architecture relies on a naive synchronous sequence. Achieving this target requires restructuring how the system handles compute, network communication, and data state. The solution relies on three specific engineering principles: prioritizing eventual consistency, shifting loads to asynchronous flows, and enforcing extreme data locality. Preventing fatal performance bottlenecks requires designing a topology that assumes latency across network boundaries is inevitable and actively isolates the user from it. The first intervention targets the runtime platform, specifically isolating CPU-intensive, high-request-per-minute bottlenecks. This animated view shows node-based services struggling. Handling large computational workloads, the single-threaded node fails to clear the request queue. Replacing it with a JVM-based service on Nile or Ninja frameworks widens the pipe, instantly draining the backlog. However, raw runtime speed is only a partial fix. Scalability. To scale effectively, services must be strictly stateless. This requires flushing local state out of the service's memory and pushing it into an external database or distributed cache. Detaching the state allows the system to scale horizontally on demand. Any instance of the service can process any incoming request without needing past context. Sustaining high throughput begins by matching the runtime to the workload and strictly decoupling computation from state storage. Addressing the network layer requires breaking linear dependencies between services. Engineers often assume that strict data consistency must be maintained across all these services simultaneously during the transaction. This sequence diagrams a linear synchronous remote procedure call. Synchronous RPCs force multi-step operations to lock up resources sequentially, leaving the user waiting. Instead, eventual consistency is the default. We break the bottleneck by injecting a Kafka message broker. The initial service logs the action and instantly returns a success signal. Heavy lifting is offloaded to downstream services, pulling at their optimal pace. The trade-off here is time. The data state across the various services is not instantly synchronized in that initial millisecond, but will align moments later. This eventual consistency is a necessary compromise, designed to completely insulate the user's experience from long back-end processing times. Protecting the 30-millisecond latency budget dictates that you answer the user instantly while resolving the full system state asynchronously. Even with asynchronous flows, the architecture will bottleneck at the persistence layer if the database design is overly rigid. Under high request rates, database-level foreign keys create severe locking contention. Avoiding them entirely removes a major source of transaction drag. This layout maps a single database cylinder splitting into separate connections. One handles incoming read-write operations, while a cluster of read-only replicas handles the outbound data. Routing read traffic exclusively to these local RO replicas prevents read-write collisions and drastically reduces query times. However, querying data still incurs a penalty if services constantly initiate remote RPC calls to retrieve information from distant nodes. We bypass this through materialization, the practice of storing a localized, pre-computed view of remote data. Instead of repeated remote pings, a copy is pushed into a local block. Pairing this materialized data with Wix cache replaces heavy, frequent synchronous network calls with near-instant local memory access. To prevent local replicas from crashing, all queries require strict index optimization, and unbounded queries must be prohibited. Speed relies on data proximity. High-performance services eliminate network latency by bringing the required data directly into their local execution context. At the macro level, physical distance introduces hard limits based on the realities of global data centers and network transit times. This global map visualizes the performance penalty of cross-data center calls. Avoiding these long-distance hops requires rerouting user-facing traffic to the nearest local data center. The strict rule is that user requests must hit a local entry point and query localized replicas, neutralizing geographic latency. When external requests hit the system at the API ingress layer, defensive design practices must handle volatile traffic volumes. APIs must enforce strict pagination, filtering, and utilize bulk endpoints to prevent external systems from pulling massive, unbounded datasets. Furthermore, we must distinguish between timeouts, where a system passively waits for a failure, and deadlines, where the system actively terminates a request. Enforcing strict deadlines kills doomed requests early. This frees up execution threads, instead of leaving database connections hanging. If specific endpoints possess wildly different service-level agreements or traffic profiles, they should be physically split into separate services to isolate the load. Defensive network and API limits act as blast shields. They protect the internal architecture from catastrophic external loads and ensure consistent operational speed. We can now trace that initial user click through the optimized system. This 3D isometric view maps the completed architecture: JVM processing nodes, read-write and read-only split databases, Kafka messaging queues, and localized Wix cache blocks operating as a unified environment. The request clears the API edge, passes the strict deadline parameters, and enters the localized JVM compute layer. It drops the workload into the Kafka queue and immediately routes a success signal back to the user, clocking in at under 30 milliseconds. The data insertion finishes safely in the background through the ATQ pipelines and the split databases, totally removed from the user's critical path. Raw speed in a distributed environment is rarely achieved by writing faster loops in the code. True scale requires decoupling workloads, accepting eventual consistency, and eliminating network hops by keeping data localized. By architecting specifically to neutralize network boundaries, we prevent delays from compounding and secure a frictionless, low-latency experience for the end user.